Today's lesson is on LHopitals Rule. We'll look at how to use the limits and LHopitals Rule to find the limits and describe the behavior functions. L'Hopital's way is a way to calculate indeterminate limits. This is where we'll look at the theory behind why the limit rules of infinity work the way they do. We'll look at the indeterminate form of 0 over 0, 0 times infinity, and infinity divided by infinity. Can we solve a problem like the limit as x approaches 0 of sine of x divided by x? When we originally solved this problem, we graphed it to find the limit and the solution. Today we'll look at how to use L'Hopital's rule. L'Hopital's rule says if f of x is equal to g of x is equal to 0, or f and g are both equal to infinity, when we take the limit as x approaches a value of f over g, then it equals the limit as x approaches that value of f prime of x over g prime of x. So this tells us that we can take the derivatives of the numerator and denominator separately without having to use the quotient rule to solve. So derivative of the numerator over derivative of the denominator. If we go back up and look at the problem that we solved originally graphically to see the limit as the x approach 0 from the left and the right were both equal to 1, we can solve this now using L'Hopital's rule. I'll take the derivative of sine is cosine of x. The derivative of x is 1. Take the limit as x approaches approaches 0, not infinity. We'll do infinity in a little bit. We get 1 cosine of 0, which is 1, over 1. So the limit is 1, which is what we originally solved when we did this graphically. So we know that the limit of the sine of x over x as x approaches 1 is, or 0 is 1. Let's do another one that we had to solve graphically before. The limit as x approaches 0 of cosine of x minus 1 all over x. Again, if we plug in 0, going back just a sec to the other one, the form of this indeterminate form would be 0 over 0. Same with this one. The indeterminate form would be 1 minus 1 is 0 over 0. So we know that we can use L'Hopital's rule to help us solve it. Take the derivative. The derivative of cosine is negative sine of x. The derivative of 1 is 0. The derivative of x in the denominator is 1. Now if we plug in a 0, we get an answer of 0 over 1. When we originally solved this, we saw that the limit was in fact 0 graphically. Now we'll evaluate one that's in the form of, we literally put in the infinity idea, it would be infinity times e to the infinity, or negative infinity, is always going to be 0. Because remember that the e function graphically always approaches 0, so this is its form. For solving it, we have to have it in a form of f of x divided by g of x. So I'm simply going to take and rewrite this problem as f of x e to the negative x is the same as 1 over e to the positive x. Take the limit as x approaches infinity of that. Again, this is a very theory-based driven idea. So when we're looking at some of these problems, we have to think about how the answer would actually look if we were to solve it by using derivative rules. So for this particular problem, if we use L'Hopital's rule, we would have the derivative of x is 1. The derivative of e to the x is simply e to the x. We notice that if we put in infinity into the problem, that it's still going to be a problem of infinity in the denominator. So we'll take the derivative one more time. Derivative of 1 is 0. Derivative of e to the x is always going to stay e to the x. So the limit is 0 as x approaches infinity, because 0 over anything is 0. You are allowed to use L'Hopital's rule and take the derivative as many times as you need to, generally only twice, in order to find your answer. On the next one, these are classic ones we learned the rules of infinity for on polynomial functions. So if we solve this, we'd have limit as x approaches infinity derivative of negative 4 minus 2x squared would be negative 4x. Derivative of the denominator would be 6x plus 5. Here's where you can see why the rules of infinity work the way they do. If we take the derivative again, it would be negative 4 over 6, which is negative 2/3. Now we learned that when the x of power is, in this case 2, the highest power of x is the same, you just take the numbers in front of the x squared terms. Here's why. L'Hopital's rule allows us to take and solve. Going back a step, this would be considered an infinity over infinity as the form. Both of the functions would approach infinity as x approaches infinity. When we look at the two-sided limits, the same thing can apply to the two-sided limits. Derivative of sine is cosine. Derivative of x squared is 2x. When you plug in a 0, notice that we're going to get, again, a 0 in the denominator. So if we take the format of what we've been learning again, and we do the answer one more time, or derivative in other words, we'd have negative sine of x over 2. Limit as x approaches 0, notice it's from the right. So if we look at and plug in a 0 here, we know that the sign at 0, going back to our rules, is going to be an answer of infinity. And you can check this graphically on your calculator as well. Same thing here. X approaches 0 from the left is going to equal negative infinity. And we know that if the limit from the left is not the same as the limit from the right, then it's no limit as x approaches that value. I want you to also think about this one graphically. So use your graphing calculator to check it. And we graph the original function, sine of x divided by x squared. The last thing we have are the indeterminate forms of 1 to the infinity, 0 to the 0, and infinity to the 0. The easy way to check that these are actually problems that use this form is anything really that has to the x power. They're pretty easy to pick out when you're looking at problems. So again, the way we're going to solve this is a set way for looking at the problem. We use the L'Hopital's rule in the process. We're going to also use the natural log function to help us solve it. As you can see from the definition, we're going to take the natural log of both sides. We're then going to take e to both sides to get rid of the natural log function, because we know e and natural log are going to be inverse operations of each other. And then we're going to take the limit as x approaches infinity. So when we're solving this, this will be considered a 1 to the infinity, because we have 1 plus 1 over x to the x. So 1 over x is going to be, we know the limit of that is 0 as x approaches infinity. So it's going to be a 1 to the infinity form. For solving it, we're going to follow just basic steps. If you use the same steps each time, you're going to be fine. We're going to call this the function right here. So I'm going to take the natural log of my function, take the natural log of what it is, so take the natural log. We're going to set this to be again our function f of x that's given here. and that's 1 plus 1 over x to the x. The reason for the natural log is to get rid of the exponent of the x. So if we do that, we know we're allowed to then bring down the power. So x ln of x as our basic function rule. In this case, we have ln of 1 plus 1 over x. I'm going to take this piece and I'm going to rewrite it as a function divided by a function, so I can use L'Hopital's rule. Sometimes you have to be a little bit creative. Multiply by x is the same as divide by the reciprocal, which is 1 over x. Now I'm going to take this problem right here, and I'm going to use L'Hopital's rule for solving it. Then I'll simplify it. The derivative of natural log of anything is 1 over that something. So it's 1 over 1 plus 1 over x times the derivative of what's inside. The derivative of what's inside would be 0 plus 1 over x's derivative is negative 1 over x squared. Okay, going back and reviewing. X to the negative 1, derivative is negative 1, x to the negative 2, which is negative 1 over x squared. All over, derivative again of 1 over x is negative 1 over x squared. Notice that the negative 1 over x squareds will cancel out, so I'm left with 1 over 1 plus 1 over x. The derivatives are found. If we take the derivatives again, we would end up with limit as x approaches infinity. So we have this piece right here. We know 1 over x. The limit as x approaches infinity of that is 0. We want to have numerical values here. So we only take the derivative of numerator and denominator once on these kind of questions typically. So we'd have 1 over 1. 1 plus 0 is 1. So the limit as x approaches infinity is 1. Now remember at the beginning we took the natural log of that. So I have to take the e to the ln of f of x. And then e to the whatever my answer was over here, which is the e to the first power. So e to the 1. So my answer is e to the first. So my limit as x approaches infinity of the function that I just created is e to the first. And that's it.